Hello, I am Saneli Carbajal Vigo, professor at Universidad del Pacífico in Lima, Peru, and today I will talk about a JavaScript-based simulation platform for astronomy, astrophysics, and cosmology. At Universidad del Pacífico, we understand that society needs citizens capable of making scientifically grounded decisions. And for this reason, we are integrating science-driven courses across all disciplines. We have students from different majors, such as economics, marketing, data science, and even law. And we believe that all of them should receive an education with an emphasis on scientific thinking. But this raises a key question: how can we engage students with this wide variety of interests? Well, we believe that astronomy, astrophysics, and cosmology can act as gateways towards scientific thinking, because in recent decades, popular science, in particular documentaries and others, and even books, of course, have captured the imagination of younger generations about these topics. For instance, topics such as black holes, galaxies, the expansion of the universe, among others, are very interesting to them, and we think that we can use them to teach them how the scientific method actually works and how they can properly use scientific thinking outside the classroom. So first of all, I will summarize very briefly what we mean by scientific thinking. First of all, you have a hypothesis, then you calculate predictions for this hypothesis, which is an idea, a model about the world, and then you observe the world, society, nature, and you ask yourself, do predictions match observations? If they don't, we reject the hypothesis, or at least we say that the hypothesis is not supported by evidence. And if they do, we accept the hypothesis, or at least we say that it is supported by evidence. So this is a very simple scheme of how scientific thinking works. But there's a step that is particularly important, and that's observation. Observation means look at the world, look at society, look at nature, understand actually what's happening, and compare what you see with the idea that you have about the world, the hypothesis. In astronomy, astrophysics, and cosmology, observation can be quite tricky because you need very sophisticated laboratories, observatories, and others. And that, of course, cannot be done in every institution, and that could not be done at Universidad del Pacífico. So we decided to implement a partial solution to this problem and have computer simulations that simulate the world and let students compare different phenomena about the cosmos. So basically, we give students some hypotheses about the world. Some are truth, some of them are actually true, and some of them are not, but they don't know that, and they have to compare the hypothesis with observation, apply scientific thinking, and realize which of them are true and which of them are not. And for that, we have created this platform which has computer simulations based on JavaScript. We have used the p5.js library, which is optimized or was created originally for education and other similar interests. And these simulations work on PCs, but many of them also work on tablets, phones, and other electronics. So I will open the platform so you can actually see how it looks like. This is 3o4cosas.com, and 3o4cosas translates to 3 or 4 things, and here you have up to 29 different simulations about the Copernican model, the observation of the sky. For instance, we have here the trajectory of the sun over the year, at different latitudes, at different dates, so they can actually observe the trajectory of the sun over the year, which is important to understand the motion of the Earth, for instance. We also have some simulations about the phases of Venus. The phases of Venus are historically important because they were studied by Galileo Galilei. And also we have astronomy, astrophysics, and cosmology. For instance, we have here a solar system creator. We have the sun or a star at the center. We can add bodies to the solar system, and we can add inclination to the orbits. We can also add belts, and we let the students create their own solar or planetary system and add dwarf planets and other kind of bodies and experiment with that. So there's this factor of creativity and also testing and contrasting information with what they observe in the universe. We have also this, for instance, it's named stellar distances. The simulation lets students upload, or the user upload a file of coordinates of stars, right ascension, declination, and distance of the star to our solar system. For instance, I have here a prepared file. If you upload the file and import the data, you have a 3D map of the positions of stars, and you can even add a star guide, so you can play here with the coordinates and the distance. And we apply this to constellations, so they understand that constellations are actually three-dimensional. And we apply this to galaxies. We apply this even to stars in the Milky Way, to have the structure, the approximate structure and diameter of the Milky Way. And later to Andromeda Galaxy, you can add as many stars as you want, and even perhaps every single point can be a galaxy and not a star, so you can apply it in many different ways. Now, these simulations are used in our classrooms. What we do is we first give students a theoretical background. We know that it's important. This inquiry-based learning must have, first of all, the guidance of the instructor. It's very important for instructors to give reliable guidance to students, to give a solid theoretical background, but this theoretical background cannot explain everything that they are going to do in the simulation. There has to be room for experimentation. There has to be room for discovery. So this approach, the amount of theory that each lecture needs has to be tailored to each particular simulation, so that we give enough to students so that they have a solid theoretical background to test, to compare, but not too much theory for them to know the answer beforehand. So it's very difficult, and we think that we have been improving in the last years. For instance, in 2024 we did a study among students, and most of them agreed that these resources, technological resources, benefited their learning. Some others didn't, of course, as we can see here in the chart, and we think that those students had these we think that these students got lost in the simulations because perhaps the theoretical background was not enough. That's why today we have very tailored theoretical backgrounds for each simulation. And we are now currently preparing more simulations. We want to create a clear path, because in our course we start from the observation of the sky. They start by observing how the night sky looks like, and from that they infer information about the solar system, and eventually about galaxies, about the expansion of the universe, and in the end they study the future of the universe. And so we want to implement more of these simulations. We want to improve even the guide that we use, the theoretical background, and of course we are also looking for collaborators. If there's anyone who wants to give advice about how to improve a simulation, new ideas for simulations, perhaps even about the appearance of the website even. You're welcomed. We are looking for collaborators, and we want to make this platform as accessible to everyone as possible. So we want to translate the platform to English as well, so that not only we can use them, but it can also be used around the world. So thank you for your time, and I hope you use the website. I hope you visit the website, and I hope we stay in touch. Thank you. Goodbye.